Okay, good morning. I'm from China Mobile, Mr. Yan Haishuang. So today we're going to talk about Linux kernel live patching. So I'm going to talk about what is live patching. Live patching, first, it's online bug fixing and can dynamically fix bugs, functions for kernels, and for example replace the function online. And for example, if we detect that there's a bug in the function or cluster function, and we can replace this old function with a new one. Or if you want to fix the bugs, and the only thing we need to do is that we replace the old function with a new one. So this is what we do. So during this process, we will not crash the system or cause a panic. And if we don't need to reboot the system, then the risk will be minimized. So why we do this live bug fixing? Well, we have to first detect some minor security bugs. For example, change the code, change the structure of the data, and these are minor bugs fixing, and we don't need to do a live patching. And also we cannot upgrade the generic version of kernel with it, and the version of the kernel, if we want to change it, that means lots of patching, multiple patching, and not all of them are applicable for live patching. If we want to add new features, we cannot do it with live patching. And so why are we using live patching? First, as we all know that there are a lot of codes in kernel. The quantities are large, and some minor bugs is inevitable, and there are some loopholes as well. And for example, mostly the online systems are using the old version kernel, so we need to fix a lot of bugs and a lot of loopholes. Option one is to upgrade the version of the kernel. That means reboot of the system. If you don't have high availability devices online, that is pretty difficult. And also, if we try to reboot the system directly in a hard way, then we have to risk interrupt, and there is the risk of failure in rebooting. Then we need help from professional maintainers and operation managers that will cause further latency in the progress. So reboot it's gonna cost a lot of downtime, and the cost is pretty high, and especially for the business sections that have a high availability mechanism. If we shut down our online business, then that's not good. That's very damaging, and some of the pods cannot accept a downtime longer than 100 ms. So we have to recalculate the reboot time needed, and we have to reschedule it. And for traditional cloud computing, we have hundreds of physical devices, and we have tens of thousands of virtual machines. Then if we want to reboot them all, that's not realistic. And we have to reschedule the reboot time, or reboot it in different patches gradually. So I have to guarantee that there's no risks for the reboot of physical or virtual devices. So we need live patching for kernel. That's why. So all of this system don't need reboot if we have live patching. And this is the reason behind live patching. So first, let's talk about trace. Well, we are using this FTrace mechanism in live patching. FTrace, what is it? It is a tracing tracer for kernel function, and if we're using FTrace, then we are analyzing certain events for kernel, for example, scheduling and interrupt. It can help us to dynamically trace the functions of kernel, and for example, the information about the stack and tracing latency. For example, if the interrupt is occupied or blocked. Well, for example, you will have to calculate the time needed for a reboot. So we have to find a kernel function, for example, the schedule. We can see on the screen that actually at each entry they will have a system call. And F entry is just a trampoline, and F entry is actually functioning as that. And if we add this trampoline, then it will track on the functions, on the time needed for implementation, and when it will be implemented. So we can add this call queue as a scheduling at the beginning of the function, and then we can achieve this purpose. And the dynamic of trace, what is it? If we're following the given message and add a call queue at the beginning of the function, that means a lot of workload for the memory, and also, for example, that means additional several millions of functions. That means a lot of overhead. So based on our calculations, it's going to affect up to 13% of the performance. So we alter our path. We chose other solutions. For example, when we're rebooting the kernel, then we alter the other orders to nopus on reboot, so we minimize the impact on the performance. So this is what we do. So if we replace the command from call queue to nopus, then this is what happened. And for example, this is the schedule function. As you can see, if we're doing the counter compiling or counter assembly, call queue has been replaced with nopus. And if we want to start the reboot, then basically that's the only thing we need to do. This is the only change we want to make. And if we set an FTrace here, and if we want to do the schedule for the function, then we need to track it down. And function graph. It's pretty similar with the function filter, and later we're gonna go through some more information about the kernel, and this is the only two commands we need to give so as to open the FTrace. So this is the dynamic. So this is the principle for the dynamic FTrace, and how can we achieve the online patching for kernel using this FTrace. So we have to go through the FTrace entry and the other live patching solutions, for example, KSFIS and KGraph. So they're pretty similar. So first we go to kpatch. And before doing the patching, we have to do scheduling in start machine, and we are using the start machine mechanism in Linux kernel, and we are setting limitations for the operation of other CPUs. Only the main CPUs are allowed to operate, and we are also doing interrupt for security checking. And if there is a conflict between the existing content and live patching, we need to exit. Otherwise, there might be a panic in the system or a crash in the system. So the live patching is not suitable for all platforms. For example, if some of the platforms are using scheduling, then obviously it's not suitable for live patching. And if we are using the dynamic FTrace mechanism, and we need to see how it's functioning. So at the entries of each function, we add this flag, which is called Q fentry scheduling, and the logic behind it is that we save some of the stack information at the entry of the function, and then we have a registered handler change the location of the function. If we use the handler, they will directly run the new function, not the old ones. So we are basically replacing the old function with the new functions, and then this is how we do the patching between old and new versions of functions. So before patching, so we need to do a scheduling for fentry, then FTrace. We need the code and save all the relevant information, and we need to get a registered handler to replace the location, the address, and return it to the new function. So this is how the patch is functioning after the patching process. So now let's talk about security check. So we have to guarantee that there is no wrong address contained. So the principle is that we will focus on different processes, different thread, and we will ensure none of the to-be patched functions are on the stack of any tasks. And we have to guarantee the function is called from start machine context, and we have to walk through all thread and check all functions on stacks and avoid any failure. And we also need to verify the backtrace address on the stack. For example, if we run this thread in function 1 and replace function 2 with a new version, and we will first schedule function 2 and then function 3, and it will not pass the security check at all. KPS live patching, we have a toolkit. We will do it through a dynamic patching process. And we have 3 modules: kpatch, build. So basically we are altering all these codes in the patching into live patching module, and all the patched codes will be re-encoded and make comparison and differentiated the functions and its patchings, and we will produce modules of the patching and coding in accordance with the alters we make.
Yes, it includes some important information about some functions. It includes the replacement functions. When the live patching is active, then we will just schedule these new functions, and also the kpatch core module. It means the point KO file. It's just provide a service interface for the patch modules to register new functions for replacement. Yeah, it's just for interface for the replacement, like the KOF file. We want to replace it with the jump. The new functions it want to be converted to, so it can achieve online replacement. Kpatch build is to generate live patching. First, it wants to compile the original kernel code. It will mark it with this function sections and function data sections, and it will rebuild the VM Linux for patched kernel. And it watch for changed objects for each objects. It will generate one by one analysis, kind of like what kind of function has been replaced and what kind of function has been added. So, and to put them aside and to link all the output objects and generate the patch mode. Yes, the patch mode module. This is the key field, how it can generate the live patching. This is the whole process. So to an overview, the kpatch build the patch module, and the patch. It can generate the kpatch test module. if you want to apply this live patching, we can refer to this one, and it is enabled. So firstly, we need to compile the original SRC, and then we have this output objects, and then we do the comparison. And if there's some abnormal ones, abnormal functions, we will want to put these abnormal ones in this object output objects, and for the kernel modules, we put this system to be enabled, so as to ensure that the live patching is enabled. So I like to do a demo. For this demo, we have a question here. I'd like to share with you on this K8S platform. And when we are generating this subsystem, there is no spice left on device error, but we have these community patches, and I can explain it to you. When it is in K8S function, we keep creating containers and destroying containers. There's a bug. The CSSIT, the technology is not decreasing. So it quickly reaches the limits, the 0.553 limit. If we want to create another container, then there is a kind of a fault here. So if we want to apply for a kernel, it's not practical. If we want to apply for a kernel, there's a lot of nodes, and if we need to update all the nodes, the life cycle can be very long. So we encourage to use the live patching technology, and it concerns some changes in the data structure. We can use the callback macro and the shadow variable function to avoid this change in the data structure. Yes, I can do this demo for you. So for this live patching, I disabled it. I can monitor the C group. These are the resources for the C group. And it keeps producing the containers. This script the memory C group resources, I have created like over 65,000, and every time I create the containers, I will always exit quickly. So in theory, I'm not reaching this limit of 65,300. But when I'm running these containers, the building of this container will fail. We can see that the number is increasing when it reaches the limits. And if I still keep building these containers, the container will be disabled. And in the beginning, you can see we have successfully built a container. Yeah, if the live patching is disabled, if I've built over dozens of them, but it has not exceeded this limit, but it failed. And you can see, we can realize with this deck, with the live patching, we can start this disabled live patching. Once we started it, you can see the container is being built successfully again. Yes, actually, the live patching is the one renovated. And we can do the online repair. We don't need to reboot the system. If we just remove this live patching, then you can see the task will fail instantly. That's my presentation today. That's not my demo. How the live patching can be enabled and can solve some issues, very serious ones. And I like to talk about the limitations on its limitations. We need to perform a human safety analysis. Yes, the smaller the live patching, the better. When there is patches which modify initial functions are not supported. And we can't use the existing codes to do for this live patching, and it's based on data function, data section, and it doesn't support the data section. Yes, this initial functions. When the kernel is enabled, they will be loaded, but they won't be used for later ones. And patches which modify functions are missing a factory core are not supported. And 80% of all CVE patches currently supported. This is very complicated. It's not supported here. And when you are building this patches, you will cause some latency. Yes, if for some operations they have high requirements for latency, it will bring some risk. And we should take into consideration of this. Thank you. Any questions? I have a question. If there is a data structure change in the kernel, can you just repeat how you build the live patching? Yes, if there's a change in its data structure. And yes, you can use the kpatch. Set a variable. Yes, this is very variable. Kind of, it's bundled with the structure. For example, if I use this structure, I will use the shadow variant to access this address. It's kind of, they are bundled together. Yes, the kpatch can provide this mechanism. If it's a very core structure, I mean, instructor. If we add LPID, it is also acceptable. I have a question. For this live patching, so it can realize the function level or variance level replacement. How can we do the decoupling of it if it depends on the logs? For example, if the function has a log, it should be careful with it. Because if you use live patching, it will cause a deadlock. We need to analyze its logic in this function. If it can cause deadlock, then you cannot use live patching. So can we do the analysis manually without the tool to perform this analysis? Yes, we can just judge manually. Yes. But for human intervention, it is very complicated, you know. It's very difficult. Yes, I mean the deadlock. They use a log DP, it's also okay. But I think it's very complicated. For some complicated deadlocks, I think we still need human intervention, like the crash and call analysis. Thank you. Hello, I have a question. You have mentioned it's talking from the perspective of developers. I'm in OM. I want to know if we have some tools to automate this process to make it more convenient for the live patching and some bug. I'm not sure if you have this tool. The kpatch. Actually, we do the packaging. If the patching is failed, then we want to retry it. Yes, that's the core technology. But in terms of the OM, you need to do another packaging yourself. Yeah, if the patching fails, we need to do another packaging. But for batching, I think you should use RPM package. Thank you. Thank you.